Okay, so let's look at this problem. This is one out of your textbook. It's a frame problem. And it asks you to determine the horizontal and vertical reactions at A and C. Now, if you look at the whole structure as a single free body, we know with one free body you have just 3 equations of statics. But at the reaction at A as a pin, you have 2. And again, a pin at C, you have 2. So again, if we try to just do the entire free body to start our problem, we're going to not have enough equations for our unknowns. So the key to this particular problem is if you look up here at B, it's also a pin. So that's a great place to disassemble our structure into 2 free bodies. 2 free bodies gives us 6 equations, and then we would have our original 4 unknowns plus 2 more at the pin. 6 unknowns, 6 equations should be okay. There's a couple different ways to work this. Do you guys have a preference? Would you like to do AB first or BC, or does it matter? I suggest that AB would be a better approach, simply because your unknowns at B and your unknowns at C, well, 2 of them are collinear. So when you sum a moment at some point along that line, you won't have to worry about those forces. So let's do that first. So I'll look at what I'll call section AB. So I'm going to draw a free body diagram of that section. So at A, I'm going to assume that I have reactions at A, and I'll say I have AX and AY. I'm just assuming directions for those, but I like to choose the positive Cartesian coordinates. And I'll do the same thing at B. I'll assume that BX is to the right and BX is up. Now, how do I handle this distributed force? Do I want to deal with it in that form? Probably not, right? So we're going to come up with a concentrated equivalent of that. So what's the area of this particular distributed loading? Yeah, it's a rectangle, so it's going to be the base, which is 5 meters times 350 newtons per meter. So what does that come out to be? 1750. So there's a 1750 newtons, and it acts in the centroid of this area, which is, again, not hard. It's a rectangle, so we know the centroid is half the distance, so that will be 2.5 meters. So from my perspective, that's a complete free body diagram. Now we can apply our 3 equations of equilibrium. As I mentioned before, it's a good idea to choose the pin to sum your moments, because since the 2 forces there are concurrent, they won't have any effect on the moment. And the other advantage here is you'll notice that 2 of our unknowns are in the y direction. So if we pick a point along that line, they won't create any moment. So I'm going to, just because A comes before B, I'm going to sum moments about A. I'm going to make sure it's in equilibrium, and I'm going to use right-hand rule as my sign convention for moments. So about A, my concentrated equivalent force creates positive or negative moment about A. I'm using counterclockwise as positive. So that would be negative, right? So I have a negative 1750 Newton force. And what's the moment arm? 2.5. Okay. Again, AY and BY do not create moment about A because they are collinear and they're passed through A. But BX does. And what kind of moment does BX create, positive or negative? Negative, right? So it's BX, and then it has a moment arm of 5 meters. So we should be able to solve for BX. It looks like it should be negative. What is that? What's half of that? 875? Now, I may have mentioned this to you before, but I want to remind you, just because you get a negative, you don't go back over to your free body diagram and start changing things. Leave it alone. Now, any time in the future that you use Bx, what value are you going to put in? Negative 875. So it'll all take care of itself. Okay. What else can I get with this free body while I'm here? I have Bx now. What else can I get?
AX.
Yeah, Ax. So I'll assume to the right is positive, and I will sum forces in the x direction. Make sure they're in equilibrium. From my free body, it says Ax is to the right, plus Bx is to the right, plus my concentrated equivalent force of 750 newtons. So I plug my negative 850 in here. What does Ax end up being? Also negative 850. Oh, I'm sorry, 875. Now, I'm going to encourage you as you work problems in the course to stop and look at your reactions or your internal forces and see if they make sense to you. Does it make sense that both these reactions really are to the left? I think so. So I feel pretty comfortable about that. Also, if you look at it, because of the geometry, it also makes sense that they should probably be equal. This force is in the center, so half would go one way, half would go the other way. So this seems reasonable. If we didn't make any mathematical errors, it seems to be positive. I think this is a good result. What else can we do while we're here? We've got one more equation, right? So what if we sum forces in the y direction? For equilibrium, it has to be equal to 0. And what does that equation tell us? It says that AY plus BY has to be 0. So we don't get a numerical answer, but we do get a relationship that AY and BY are equal in magnitude, but opposite in direction. That's a good thing to know. So later in our problem, if we say get BY from someplace else, we're going to know AY. So 2 down, how many more to go? 4. But we're done with this free body. So the next one we can do would be, say, section that goes from B to C. So let me sketch that one real quick. Alright, so this is the B point on that. Now, since I've already made these assumptions for Bx and By here, they have to be what on this body? Equal and opposite. That's critical to the success of this free body diagram. Now, we already know from our previous calculations that Bx is negative, but I'm not going to make any changes here. I'm going to go off my original assumption, and I know that it's going to be equal and opposite here. Now, when I use this equation for Bx, I will put in my negative value. So what else do we know? At A, I'm also going to assume 2 unknowns. And again, I'm back to my kind of positive sense. I'm sorry? C, thank you. Unfortunately, I can't erase this, but I think I'll block it out. Thanks. Okay, are there any forces on this free body? External forces that we can see? Doesn't look like it. So I have dimensions. Now I will go ahead and circle Bx just to kind of remind you that I really know that value. So I want to take advantage of that. So I would not suggest summing moments at B first because you're going to get one equation and 2 unknowns at C. But if you sum moments at C, you'll get one equation and 1 unknown, By. So let's do that. So again, I'm going to use right-hand rule for my sign convention. And I'm going to sum the moments at C, make sure we're in equilibrium. So let's do that. Summing moments about C, we know Cx and Cy are 0. Are not going to create moment. So what is Bx? Is it going to create positive or negative moment about C, the way I've drawn it here? Positive. And what's the moment arm for that? What's the distance? 5. What about By? Positive or negative? Positive. So positive moment, By, and its moment arm is 4 meters. So we should be able to solve for by by plugging in this negative 875 here. So multiply that times 5 and divide it by 4, and you get what? 1,000. What did you say, Mr. Kimmett? 93.75. Anybody else get that? Solving for by. I get a positive value, so I assume by, that's the right direction for by. Anybody else get that?
What did you say?
1,090 what?
1,092.75.
Are you getting that? Okay, so 1,093.75. That's a little too precise, but I'll just leave it like that. In this course, we'll just do kind of 3 significant figures will be good enough. So this 1,094 would be accurate. Now, I will remind you that in mastering engineering, a lot of the questions will tell you to do it with so many significant figures, and you have to follow their rules. If not, you might get asked to enter your problem again. Oh, also notice that since we have by, we also have ay. So what's ay equal to? Minus this, right? So now we have 1, 2, 3, 4 things. We just need the rest. So let's finish. We can now sum forces x and y. It doesn't really matter. I'll sum forces in the y to start. So summing forces in the y direction, making sure in equilibrium. I've got by acting down. I've got cy that's negative, plus cy acting up. Before I even put any numbers in there, it just says that cy is equal to by, right? And what is by? So cy is also going to be 1,093.75 newtons. And the last thing I can check is sum forces in the x direction. Right? And again, for my free body diagram, I have bx to the left, so that's negative, and cx to the right, that's positive. So that says that cx is equal to bx, and bx is negative 875. Okay? Does that make sense to us? Well, let's look down here at the very bottom. So when we're all done, we're looking at the total structure. Let's look at reactions at C. With this force from the left, how do you think the reactions at C should be? Do you think C should be pushing up or pulling it down? Probably pushing it up. So that means that CY should be acting up. I assume CY was up, and hey, I got a positive value. That seems to be reasonable. Think about it this way now. If I'm thinking about, what if there was no support at A, how would this structure move about C? Would A lift up or go down? It'd probably lift up, so you should probably expect AY to be down. And did we get AY to be down? Well, I assumed it acted up. Where is AY? And AY is equal to negative BY, so it is down. So that makes sense too. What about the X components here? With this force pushing from left to right, I imagine both these reactions are negative. So what did I get? Well, I got BX was negative, and I got CX was negative. So the result seems to be reasonable. And I encourage you to take that extra time and kind of just check the rationale and see if you've got the right directions. That could help you as you move through. If you lose a sign here or there, it's just going to propagate through the problem. So anytime you can stop and use your insights to kind of help validate your answer, I think the better you'll be. So any other questions? All right.